Great. So welcome to lecture number 14 in ME303 heat transfer. So today we'll continue our discussion on 2D heat conduction that we started yesterday. So I'll just quickly recall as to what we were doing yesterday. So we had taken a problem which is a rectangular cross-sectioned rod. The dimensions, so the origin is here. So this point is my x equals 0, and this one's x equals L. So this is my x and y coordinate system, and this is my this is y equals w. Okay, it's a rectangular cross section, and this one's y equals 0. Okay, so this is the cross section of a rectangular rod which is maintained at temperatures T1 on 3 boundaries and T2 on the top boundary. So T2 in this case we are assuming is greater than equal to is greater than T1. Okay. Yesterday we defined a non-dimensionalization which was based on theta, defined as t at any position. So I'll call it x minus y minus t1 divided by t2 minus t1. Okay, so with this theta that we have defined now, so we can have an equation. Our equation becomes in theta and x and y, theta as the dependent coordinate. But the good thing here is that theta on the boundaries, on these 3 boundaries, will become 0, and on the top boundary we'll have theta equal to 1. Okay, and on the inside we'll have theta varying between 0 and 1. So that's a good thing. We have normalized the coordinate, and the equation that we started with was again our 2D heat conduction problem. So in this case, that became the Laplacian of theta was equal to 0, or del 2 theta by del x2 plus del 2 theta by del y2 was equal to 0. Okay, so this is what we started with, and then we used the method of separation of variables. So which resulted in which we assume that theta, which is a function of independent coordinates x and y, can be written as a function capital X and a function capital Y. You see, these are I mean, this is an assumption we took. I mean, it may not be true, but actually in this case we know that it comes out to be true. So when we substitute this, we get 2 ODEs, ordinary differential equations, and these ODEs, when we solve them, we get a solution, and then we substitute that back into theta. So our theta that we finally got after doing a series of steps finally came out to be C1 times cos lambda x plus C2 sin lambda x multiplied C3 e to the power of minus lambda y plus C4 e to the power of lambda y. So this is the theta we had got after solving the equation using the method of separation of variables. This is exactly where we stopped yesterday. So do we have any questions till this point? Okay, so if there's no question, then let's proceed. So what we have to do now is to find the 4 constants. Okay, so for finding the constants, as you know, that you have to use the boundary conditions. So in this case, let's use our first boundary condition. So which is theta at x equal to 0 and any y, which is this this boundary. So I'll put this red color here just to make sure which boundary we're talking about. So theta at x equal to 0 and y is 0. That's a left boundary. All right, so let's substitute that in our expression number A that we'll call. So if I put x equal to 0, what I get is so cos 0 becomes a 1. So we get a C1, and sine 0 is a 0. And then we have C3. Y this is for any y. It's a complete left boundary. So it's for all values of y that we can have. So this becomes C3 e to the power of minus lambda y plus C4 e to the power of lambda y. And this is 0. Okay, remember that this has to be 0 in all cases. Okay, so the only way this can be 0 is, well, remember we have to find the values of the constants. So one both are 0. But if that is the case, then theta becomes 0, right? So if C3 and C4 both are 0, then theta becomes 0, which is not the case because on the top boundary we have theta equals 1. So that won't satisfy the top boundary. So this cannot be true. So the only thing that we can have here is that C1 is 0. Okay, so if C1 is 0, then this above equation is satisfied, and then what we'll get is we will lose the C1 cos lambda x term because C1 is 0. So every time I apply a boundary condition, I'll update the overall expression for theta. So now my theta is the updated version of theta is C2 sine lambda x times C3 e to the power of minus lambda y plus C4 e to the power of lambda y. Okay, so that is my updated version. So I'll call it A1. Is that clear? So let's move on. I'll go to the next page now. The good thing is now I'll be able to share this these PDFs with you as well along. Okay, so let's apply the second boundary condition. Let's see if we can copy the figure somehow. Perfect. Very good. So I can keep the figure on my right just for reference. Okay, so let's apply the next boundary condition. So last time we called it BC1. So let's let's call it BC1, and then I'll call it left. Okay, that's easy to remember. So then I'll call BC2, which is the bottom boundary. Okay, so that is this one. So in this boundary, what we have is theta at any x for y equal to 0. That's the bottom boundary. So I'll substitute this in A1. That's the updated version of my expression for theta. So when I substitute that, then remember A1 only had the C2 sine lambda x term. So I'll have a C2 sine lambda x times, then we had a C3, and then if I go back, just to recall, then we have C3, and then we have e to the power of minus lambda y, but y is 0 here, so this becomes e to the power of 0, which is 1, and the same happens for the second term as well. Okay. So this becomes C3 times 1 plus C4 times 1, which is 0. Okay, we have to satisfy this condition now. Now remember that in this case, there are two conditions possible for the constants. One is that C2 is 0, but if C2 becomes 0, then the whole theta becomes 0, and that does not satisfy the top boundary, which is this one. Okay, so that is not possible. So the only thing possible is that we have C3 plus C4 is equal to 0. That means C3 equals minus C4. Okay, so again, we have got rid of one more constant. So my updated version of theta now becomes C2 sine lambda x plus, times. We have, so if I substitute C4 as minus C3, so then, so now we can have a look at the expression. So if I substitute C4 as minus C3, so I get a C3 out. So I can take my C3 out, and then I power of minus lambda y minus e to the power of lambda y. Okay. So this is the expression, the updated expression for theta that we have now. You can see that we have C2 times C3. So that's a product of two constants. So now we can call that another constant, which we'll call just C. I'll just call it C for simplicity. Is that clear? All right. So let's move on from here. So we have this theta with us. Sorry. So what I can do now is I still haven't found the value of lambda. Okay, so if you recall, then and this lambda appeared when we assumed that for the ODEs for the left hand side and right hand side to be equal, there has to be lambda. Okay, so that lambda is not known, and lambda has to be found out somehow. But we still have two more boundary conditions left, and that is a good thing. Okay, so we have two things left now to find. One is this C, and the other is this lambda. So we have two more conditions. So let's use them. So the third boundary condition we use which is let's use the one on our right. So which is I'll use the green color now. So which is this one. So for this boundary condition, we will have let's use the further updated expression. So I'll call it A2. Okay. So this condition is theta at x equals L and any y is equal to 0. Okay, so when I substitute that, so when I substitute my theta at x equal to L, so in A2, okay, so I'll call it substitute in A2. So let's substitute x equals L here. So it becomes C times sine lambda L, and that times minus lambda y minus e to the power of lambda y. And this is 0. By the way, I just I'm sure you remember what hyperbolic sines and cosines are. So we can write this expression. I'll just recall for myself as well. So we have the same way we have e to the power of I theta as cos theta plus I sine theta. So we can write, if I wanted to write sine theta, what I'll do is I'll write e to the power of I theta minus e to the power of minus I theta. So that becomes theta plus I sine theta minus cos theta, and then e to the power of minus I theta, and that becomes sorry, this becomes a plus and this becomes a minus. Is that right? Can somebody please check?
No, sir. Should be
The
minus
cos of
cos
minus.
theta and plus, because minus theta is of cos is equal to cos theta.
Right. So
So
should
it
I have
goes
a
into
minus
minus.
here, right?
Yeah, and with plus in front of the sign theta.
Plus here, right? Right. So because e to the power of minus I theta is cos of minus theta, which is cos theta, and then sine of minus theta is minus sine theta, right? Use this and this, then we can find this expression. So what this gives us is this becomes 2I sine theta. Right? So similarly, we define the hyperbolic sines and cosines as well. So I can write um, if I use e to the power of lambda y minus e to the power of minus lambda y, that gives me twice the hyperbolic sine of lambda y. Let's make it a bit more clean. So that's how we define these hyperbolic sines and cosines. What we see is that I can actually replace as twice sine hyperbolic lambda y, but we have to have a negative sign here because we had a minus e to the minus lambda y first, so we get a negative sign here. Okay, so again we have a constant 2 and we have a minus sign, so we can absorb that into my c. Okay, c is again just a constant. I don't care if that contains my minus 2 as well. So that simplifies things a bit. All right. What we were doing was we had to make this 0. Okay. Again, remember that we the only way we can make this 0, we make c 0, but that is not possible. Otherwise, everything becomes theta becomes 0, but that does not satisfy the top boundary. Then the other thing we can have is this sine lambda L that becomes 0. Okay, but this hyperbolic sine cos sine lambda y cannot be 0 because then it's 0 for all the values of y. Okay, and which is not the case. Otherwise, it does not satisfy the top boundary. So what we have is we have this. See, let me replace this a2 as well, just for clarity. Okay, so this means that my sine lambda L has to be 0. And remember that this is satisfied for my lambda L is equal to n pi, where n is starts from 0, but we won't take that to be 0, because if n is 0, then again we theta becomes 0 for all the values of x and y. So this is n is 1, 2, 3, and dot dot dot. So this means my lambda is n pi by L. Boundary condition 3 to find the value of lambda now. Okay, so one more constant done. So let's update our expression for theta now. So theta now becomes c. So I'm using a2, which is this one, and then I have sine lambda x. So all instances of lambda will be replaced by n pi by L. So this becomes sine n pi by L times x, and then we have hyperbolic sine of lambda y. So lambda is n pi by L times, then you have y. Okay, so this is my a3, further updated expression for theta. So I've got one more boundary condition left, which is the top boundary, which is so let's apply that. So we'll call it BC4, which is the top boundary. So the boundary condition on the top says that theta at all values of x for y equals w is 1. It's not 0, it's 1 now. Okay, so let's substitute that in A3. So we get c times sine n pi by l times x times the hyperbolic sine of n pi by l times w, and this is equal to 1. Okay, so we have to use this condition now to find the value of c, and once we have that, we will update our expression A3, final expression for theta, in terms of all known values. There will be no constant which will be unknown. Now this is interesting, this part, because actually this is one thing I had to do. So remember, in this expression A3, we have lots of values of n. Okay, we don't have just one value, so we have lots of values of n. So I should have I missed that. So for each value of n, we get one solution. Okay, because as I said that n is taking integer values from 1 to infinity. So this means that I have lots of solutions, and this equation that we started with was a linear linear partial differential equation. So that means that if I have two solutions, and then a linear combination of those solutions is also a solution to the partial differential equation. Okay, that's the good thing about linear equations. Well, linear homogeneous equations. So what happens is, then the linear combination. So the most general solution for this equation actually is this solution, which is a combination of all the solutions for different values of n, and for each solution we'll have a different constant. Okay, so the amount of contribution of each solution may be different. So a general sense is to say that the constant for each independent solution for the overall linear combination is when you have two solutions, you say that the general solution is C1 times first solution plus C2 times second solution. That is exactly what we are doing. So we are keeping each coefficient of the solution to be different. So that is what A3 is. So here I should be writing this, and there's a summation over n. Okay, so now our job is to find the CNs, lots of constants. So hopefully we can find that from this equation. Now here, to find this, we have to use an idea of orthogonality of functions. Okay, so I will put a dashed line here because I'll have to recall some more mathematics on functional analysis. Okay, so you have, I'm sure you have done vector, you've read about vectors, linear algebra. So you have seen that you can have basis vectors, and you know what the meaning of basis is. So basis is a set which are, if you call it orthogonal basis, then that means that you can write any vector as a linear combination of the orthogonal basis. Okay, so this discussion that I'm having is independent from what I just to help you with an expression. So in functional analysis, functions also can be vector spaces. So that means I can write a function as a linear combination of other basis functions. Okay. This idea again, have you heard about this idea in your course in linear algebra?
Yes, sir.
Good. So then the whole idea of Fourier series is actually based on that. Okay, so the idea of Fourier series is that you can write any function, any nice function, as a sum of infinite sines and cosines. Okay, so these sines and cosines form one basis, and the sines and cosines, the good thing is they are orthogonal bases. Okay, so what we can do is we can write a function, let's say g of x, a linear combination of let's call it an as the constants, and then I can write my f fn's. So fn's are the basis functions in this case. So I can write a function gx as a linear combination of the basis functions fn. And remember that these, in this case, we are assuming that these fn's are orthogonal. Now in vectors, you know, the orthogonal, the meaning of orthogonal is that the dot product is 0. In functions, we have to define a dot product or an inner product or a scalar product. Okay, so we define for functions, for in this case, we define it on the domain. So our domain here is, in this case, is talking about, well, in this case, let's call the domain from 0 to L. Okay, let's say our domain for the function fx and gx are 0 to L. Then we can say that this means that if we have f m x times fn x dx, so this is how you define the scalar or the inner product equivalent to a dot product in your vectors. So what we say is that this thing is equal to 0 if m is not equal to n, and this is equal to, well, this is not 0 if m is equal to n. Okay, so it's similar to saying that you have two vectors, ei dot ej, and if I is not equal to j, then the dot product becomes, equal to j, then the dot product becomes 1. That is for orthonormal basis. So the dot product of 1 with itself is 1. But here we are not assuming it to be normal. Normalized, but we are assuming that to be orthogonal. So this condition is true. So this is true for our case as well. So we have taken fn's, the bases, in such a way so that they are orthogonal. So if that is the case, then what I can do is I can on both sides multiply by, let's say, f mx. So this becomes summation n goes from 1 to infinity a n, then I have fnx, and then I have fmx, because fm is just one, m is just particular value. Okay, so it can go inside the integral, so summation, sorry. Integrate this from 0 to L. So this also integrates from 0 to L. And now what we see is on the right hand side, I can take the summation out now because summation is over n. And then we have, well, an can also be taken out. Then we have integral 0 to L fnx and fm. So you can now expand this summation. Okay, so this becomes f1x, fmx, and so on. And we'll also have one term where we'll have fm times fm. Okay. So what we'll see is, from the idea of orthogonality, that the summation will be non-zero only for one of the terms. For all other terms, it will be 0. Let's go to the next page. So what we'll see is that ultimately we'll have 0 to L fmx gx, and this is equal to, we'll have lots of terms, so I'll call it a1 integral 0 to L f1x fmx, and so on. Plus we'll have another term where we'll have am integral 0 to L fmx dx. Dx is there. And then we'll have lots of terms. So all these terms will be 0 except this one. So all of these will be 0 except this one, from the idea of orthogonality. So what we finally get is an expression for am. Okay, so am becomes integral 0 to L fmx gx dx. divided by integral 0 to L fmx fmx dx. You can absorb that. And remember that the domain size is known to us, the function gx is known to us, and these fmx's are also known to us. So what we're trying to find is the coefficients a n's. So this expression helps us find one of the coefficient, and you can put different values of m here, and then you can integrate the expression on the right hand side, and you can get the values of the coefficients. So this is our discussion that we briefly started on functional analysis. My expression now here. So let's see what our uh, values are. So here, this is my gx, which is just 1, and I'm writing that gx as a sum of different. So the fn's or the functions are this. So this is my fn x. So sine pi by L times x, sine 2 pi by L times x, and so on. So for different values of x, I get different functions, and my an is basically combined. So this and this together forms my an. It's a constant. I mean, of course, sine h by L times w is also a constant. So that can be taken inside the. So I can call that as some other bn, if you want to call it. Okay, so using the same idea, I can find Cn times sine hyperbolic, sorry, n pi by L times w. Just checking that. Yeah, and then we have this replaces my a. Well, should I use m here? Just for. And this is equal to the ratio. In this case, my domain for fn, which is sine n pi by L times x, is actually from 0 to L, because x varies from 0 to L. So this becomes integral 0 to L, and my fm is sine m pi by L times x times gx. Gx is 1, and then the denominator is 0 to L. I have sine square m pi by L times x, and that is again multiplied by dx. Okay, so to find my cm, I can now also take this sine hyperbolic term on the denominator. Okay, so this gives me the value of the constant cm. So I can substitute this. Well, you can replace n with m with n, and you get cn. Doesn't matter. And I can substitute that in my expression. Sorry, a3, and I will get the final expression for the theta as a function of x and y. So I'll stop here with at least this discussion. So I'll just call it substitute and substitute in a3 and get the final expression for theta as a function of x and y. Job done. Any questions on this? All right. So this completes our discussion on the analytical solution for 2D heat transfer. Let's plot this and see what we get. In fact, I mean, the integral actually simplifies to a very simple expression, which this simplifies to twice okay, so it simplifies to a twice minus 1 to the power m plus 1 plus 1. So it alternates. So for an even value of m, we get 0, and for an odd value of m we get a something. That's 2 by 4 by m pi times the sine hyperbolic term. So when we substitute that, what we see in this case, let's draw our domain again. Okay, so remember that we had our theta equal to 1 here, and theta was 0 on all these three boundaries. So what we'll see is that the heat flows from the top boundary downwards. On the center line, we have so on the center line we have a straight line because it has to be symmetric. So the heat flux line is vertical, and otherwise we see that we get something like this. Okay, it has to be symmetric. I'm not drawing that ways. Okay, so heat flows from the top all the way to the sides, and this is what we get. And if you were drawing isotherms for temperature, then the temperature isotherms will be perpendicular to this, because you know that the um, Q is nothing but grad T. So grad T is perpendicular to the isotherms, the constant values of temperature. So they will come out to be something like this. Again, they have to be symmetric. I didn't draw them that way. So these are isotherms, and these green lines are the heat flux vectors. So at any you draw the streamlines. At any point you draw a vector, and that will give you the heat flux vector at the direction of that vector at that point. Okay, so that gives us some idea of how the heat flows in this situation. Okay, any questions? All right, so let's move. I would really want to finish this discussion, this chapter today. Now, as I said, that this analytical solution that we worked with, I mean, this is helpful for testing our codes, which are generalized, because the real problems we get usually do not have analytical solutions available for it. So we use them for testing, and the other thing is we use them as first approximations. So if we have to approximate or estimate the heat flow or the temperature distribution in a given situation, we can approximate that situation as the closest rectangular rod, for example, and then we estimate, and then we move on. Once we have more time and resources, we can spend more time by solving the computer codes numerically, and then we can get more accurate estimate. So we said that we can use it for testing the as engineers, we spend a lot of time working on developing these codes, testing codes, and implementing them on high performance computing clusters or supercomputers, and then developing algorithms for making these distributed or parallelized processing more efficient and accurate. Okay, this is, in fact, if you read about the development of supercomputers, one of the major applications which drove the development of supercomputer was solving fluid mechanics problems. Okay, weather prediction. It's been a major application of using supercomputers. Well, AI and machine learning have come up recently, but in the past, supercomputers have been driven by fluid mechanicists and heat transfer analysts. So we have a significant contribution towards the motivation behind developing supercomputers. And of course, I mean, people who have the motivation also contribute towards it. So a lot of mechanical engineers have worked towards the algorithm development and so on, as if you read them. And in fact, we are one of the major users nowadays as well of supercomputers. In fact, here in IIT Mandi, a lot of engineers use and well, they manage the high performance computing facility as well. So we should at least talk about what very briefly about what sort of process is involved in converting a problem which is solving a partial differential equation to a problem that can be solved using computers. Okay, so computers can only do calculations. They can add, subtract, multiply, and divide. So what we have to do is this partial differential equation that we had. So I'll call this. Okay, so this domain that we had, we wanted to find the value of theta at each and every point on the domain. Okay, so ultimately the solution we got, theta is a function of x and y, is valid. You put the value of x and y, and then you get the value of theta. So when we do it as using the computational methods, what we say is that instead of finding the value of theta at each and every point continuously inside the domain, we'll be happy if we can find value of theta at some discrete points in the domain. So what we do is we create a mesh, and these grid points that we get are the points on which we will calculate the value of theta. Of course, on these points, the value of theta is known as the boundary condition on the boundary points. Okay. So we say that we will be satisfied if we can find the value of theta on these discrete points in the grids of the mesh. And of course, I mean, if you want a more accurate solution, you can take closer and closer. You can take a more finer mesh, but that means you'll have to solve. The computer will have to do more work. So there's a trade-off between the accuracy you can get versus the computational time it will take to solve the problem. But this is the general technique that we use. And then this equation that we earlier had this d2 a partial theta by partial x squared plus partial theta by partial y squared equals 0. So that's the equation we were solving. So what we do is, well, there are different methods. So I'll talk about the finite difference method. So as the name suggests, what it does is it converts the differential equation to a difference equation. Okay, so it converts our partial differential equation a set of linear equations that can be solved, and then we can get the value of the theta at these different values. So ultimately what we want is we want to go from here to a system A x equal to b, where this x vector is a vector of unknowns, which is basically our x vector is the unknowns theta 1 1 theta 1 2, where this is 1 comma 1, this is 1 comma 2, and so on. So we have a complete vector of unknowns of the temperatures or the theta values in this mesh. Okay, so the computer can easily solve Ax equal to B using different methods of linear solvers. So what we do as computational analysts is to convert this equation to a difference equation. For that, we have different methods available. One's called a finite difference method, one's called a finite volume method, and the other one's called finite element method. So these are the most popular methods available for converting our partial differential equation to this kind of a coupled linear or a system of linear equations. Okay, so I'll talk about the finite difference method briefly. So what it does is, I mean, the idea is that if you have, just a derivative, let's say dt, or sorry, d theta. So if you had just a first derivative of d theta by dx at, let's say, I want to find it at this point. So what I can do is, I'll call it at some x naught and y naught. Then what I do is I take 1 point forward and 1 point backward. So I call it theta at x naught plus delta x comma y minus theta at x naught minus delta x comma y. Delta x is this grid size, and then I divide that by twice delta x, because what I've done is I've taken this value of theta minus this value divided by twice delta x. Okay, so that's the basic idea of using a finite difference method, that you convert uh, a derivative to a difference. So you do the same thing. If you have a second derivative, you have to apply that again. And if you do that, ultimately what happens is you get an equation. You get lots of equations, because this equation that you have, PDE, is satisfied for each and every point in the domain. Okay, so you write this PDE. Well, if you have n times m points, you write it n times m times, and you will get n times m equations in unknowns of theta, and then you will solve them, and this you will get the final value of theta. There's a whole course that is offered here in IIT Mandi. It's called computational fluid dynamics. Talk any more about this method, but you should at least know the ideas behind these methods. Okay. I think I should stop here with the finite with chapter number 4. Anyone who has a class, because if you give me a couple of more minutes, I can demonstrate how this method works. I'll take 5 to 10 more minutes, and you open Matlab and show it to you how to actually use. I mean, it's very easy, it's very straightforward, how to quickly solve the problem, exactly the problem that we have solved using Matlab, and then we'll plot isotherms and so on in front of us. So is there anyone who wants to leave? Otherwise,
Sir,
I will do it next.
so I have a class, but I can watch it in the YouTube video. So you can carry on.
Perfect. So thank you very much for that. So I will continue then. I have just one video created for this lecture and completes the discussion. So thank you, Jatin. So you can have a look at the video later. So let me quickly connect my computer screen so that I can comfortably. I'll stop sharing my screen now. Give me a couple of seconds to start up Matlab. So I'll start sharing my screen now again. Right. So can somebody please confirm if you can see my screen, my MATLAB screen now?
Yes, sir.
Yes, sir. Perfect. So I've got the MATLAB prompt here. So what we do is, I mean, there's lots of functions available that you can use to you can use in this for this purpose. So what I will do is I'll use a toolbox. So MATLAB has lots of toolbox, and this toolbox is called PDE toolbox. So if you write PDE tool, it opens this toolbox view. And so what the first thing you have to do is you have to define, I mean, draw the domain, okay, how it looks like. So first, I mean, actually, I've forgotten how to use it, but it's so intuitive that it's easy to recall. So first, I will draw a grid so that it is easy for me. Let's say that we want to have a domain. Let's think this is to draw a rectangle. So I start with 0, 0, which is this. And then remember, x went from 0 to L. So let's take L and W both equal to 1. So it's a square domain. So this is, well, it's not exactly a square. Let me delete it, and then I can actually write snap. So what it does is it snaps to the grid. That becomes easier for me. So now it is a size 1, 1. Okay, so it actually takes it as square rather than a rectangle. All right. So this is step 1. Then the next step is to create a mesh. Remember, we said that we have to create these mesh nodes on which we'll solve for the value of theta, rather than continuously on the domain. So for that, we have to sorry. First, we have to write boundary conditions. So the left boundary, so it says whether you want the condition to be Neumann or Dirichlet. So in our case, it's Dirichlet. And remember, u is the unknown here. So theta can be replaced with u. So the boundary condition is h times u equals r. So in our and u and r is equal to 0. So by default, they have used theta equal to 0 here. So I'm happy with that. I can check the bottom boundary as well. So I double click on the bottom boundary. It's again the same. 1 times u equals 0. I think the right hand side would also be the same. And then on the top one, I have to replace that with h times u equals r. So r is equal to 1 in this case. Okay, so that's theta equals 1. So this is, we have defined the boundary condition on the 4 sides. Now we have to define a partial differential equation. Remember, we are solving the heat conduction equation. So heat conduction equation is an elliptic equation. Okay, I mean, again, PDEs are of different types depending on the coefficients and all. So in this case, let's look at it. So it's actually very equation where it's called divergence of C times grad of U. So C is your thermal conductivity, and C times grad U of divergence plus A times U is equal to F. So in this case, our equation is Laplacian of theta equals 0. So F is 0. Then this A constant is also 0. So this becomes minus divergence of C times grad U plus 0 equals 0. And then C can also be, C is 1. Okay, so for these values of C, F, and A, what I get is minus divergence of gradient of U is equal to 0. Then again minus is gone because you can cancel it. So we get divergence of gradient of u is equal to 0. That is the Laplacian of u equals 0. All right, so this is the equation we want. And then we have defined the equation. So you can see that I'm following these steps correctly. So after the PDE, the next step is to push to initialize mesh. So I can just press it. So it has automatically created an unstructured mesh here. Okay, so when the earlier I drew a structured mesh for you, those rectangles, but now it's unstructured. So it's much easier if you have an arbitrary shape domain size boundaries. You can define an unstructured mesh which fits quite well with the arbitrary shape domains. Okay, so that's the next step done. And the next one is to push to refine. So I don't want to refine that right now, so I'm happy with this. And this equal to sign means push to solve. That's it. You can see that it has solved the equation and then push to specify PD solution plot. Now it's telling me that I have to draw a color plot for U. So U is nothing but temperature. Okay. So I can also show the mesh. I can draw the contours. Temperature contours. U is nothing but theta, the temperature. So you can see the temperature contours. You can change the number of levels of contours. Okay, then you can also draw the heat flux. Heat flux, remember, was Q was minus K grad T. Okay, so you can plot I think arrows, because heat flux is a vector. So I don't want the contours of temperature now. I want the arrows of minus grad U. Okay, heat is minus K grad U, but K is just a constant here, so minus grad U. And then you see that it plots. You can see I don't know if the size is visible. Yeah, you can see the center one goes straight, and the ones here you can see if you draw a streamline, it goes from top to left. There's plenty plot animations and so on, but I just wanted to show you that you can very easily use Matlab for solving heat flow problems. Okay, so in the future, when you solve real world problems, you can always go to Matlab and solve problem, get some estimate. And let's say now I want well, let's go back to our contours. So you can see that these contours are not very fine. I mean, there is this jagged here, and that is because our mesh is very coarse. So what I can do is now now that computer takes time. So I did a first quick dirty task, and now I can refine the mesh. Okay, so I can now refine the mesh and then solve it again, and now you see the contours are much better. I can refine it further. I can solve it, and now you can see that they are amazingly smooth now. So this solution is now tending to the solution as you refine the mesh further, but I won't do it further, otherwise my machine will start complaining because it will have to do a lot of processing. Good. So I will stop here unless you have questions about 2D heat conduction.